Welcome back. In this lesson, we're going to talk about one of the key inputs to the gradient descent function. And this is the learning rate. So let's add a big section heading in a markdown cell. So I'm going to click on this cell here, change from code to markdown, add one pound symbol, and then write the learning rate. Scrolling back up to where we've defined our gradient descent function, let's take another look at our inputs. Previously, we've modified our Python code so that the inputs would include not only the derivative function and the initial guess, but also a multiplier, precision, and the maximum number of iterations. So far, we've changed up the initial guesses and analyzed the impact that this had on the algorithm in different situations, on different cost functions. But we've not really messed with the multiplier, and this is what we're going to do now. So what does the learning rate actually do in our algorithm? If we look at our update step, namely this line right here, we can see that our learning rate, which I've called multiplier, is multiplied with the gradient. The gradient is the value of the slope of the cost function, and the multiplier is just a constant. But together, they determine how big of a step we take. So if you remember with the gradient, when the slope was steep, then the gradient was a large number, and we take a big step. And similarly, if the multiplier is large, we also take a big step. So at the moment, we've got the multiplier set to a default value of 0.02. Now this might be a good time to maybe pause the video and think about what would happen if we picked a different value. Say, what would happen if this value was really, really small? And what would happen if the multiplier value was really, really large? Now, I'm going to illustrate the effect of the multiplier taking our second example. This was the g of x function. I'm going to take this cell right here. This was the cell that generated our graphs and plotted our scatter plot for our gradient descent on the g of x function. I'm going to copy this cell right here with the shortcut, and I'm going to scroll all the way down to our learning rate, and I'm going to paste the cell below. I probably don't need this cell up here right at the moment, so I'm just going to take this one and move it up, and I'm going to modify it a little bit. I'm going to add some print statements below our charts at the bottom. The first print statement I'm going to add is the number of steps. And if you recall, this was the length of this list, the length of list underscore x. So we'll write len parentheses list underscore x. The other thing that I'm going to modify is the initial guess that we've got. So I'm going to change this to 1.9. And I'm also going to add a multiplier here. So I'm going to add multiplier equals, I'm not going to change the default value just yet. Let's just have it at 0.02. And since I haven't run my notebook in a little while, I'm actually going to go to cell and run all instead of running just my latest cell. And then I'm going to have to scroll all the way down to the bottom. And there's our output. So it works as expected. So if I start at 1.9, which is right here, then the first step that we take is fairly large, right here, and then we slowly move down to our minimum. And at the moment, all it takes is 14 steps to get to the bottom. Okay, so this works as expected. Now let's have a little bit more fun with this. So I'm going to change our function call to have a maximum of 5 iterations. So I only want our loop to run 5 times. And then I'm also going to change our multiplier from 0.02 to 0.25. And then I'm going to rerun this cell, and then we can have a look at our chart. So what are we seeing here now? Our multiplier is increasing our step size, and we see our algorithm bouncing around on this function. So this is very, very different behavior from what we've seen before. But let's take this to an extreme. I'm going to scroll back up to our function call and change the maximum number of times that our loop will run from 5 to 500. And I'm going to hit Shift Enter. And scrolling down, we see this. The whole chart is turning red. Yeah, we're bouncing around all over the place, but our algorithm is never converging. In fact, our loop at this point has run 500 times. In contrast, we were at 14 earlier in the number of steps? So this is very interesting, right? What can we learn from this example? In almost every situation that we've illustrated previously, we've converged between 20 or 60 steps, remember? This time, our loop ran 500 times, and the algorithm still didn't find the minimum. So what we're seeing here is that if we're not careful, we can get into a situation where our algorithm isn't converging, and it just might continue going and going and going. And this kind of brings us back to our discussion about Python for loops and Python while loops. Let me scroll back up to where we wrote that code. Here we go. Now you might remember that with a while loop, you as the developer have to take extra care with your terminating condition. What's the terminating condition? It's whatever follows the while keyword right here. So if the logic in this terminating condition isn't formulated well, then it's very easy to get into a scenario where you're never exiting the loop. And then your Python program accidentally ends up in an infinite loop. In other words, with a while loop, you as the programmer need to think of the corner cases and include the logic to stop your loop from running longer than you intended to. Now, I know in this example, if you're looking at this code, this seems really, really trivial, but infinite loops happen maybe more often than you expect. Let me show you an example. We could have written our gradient descent function with a while loop instead of a for loop. This is our gradient descent function as it currently stands, with a for loop and a cutoff point determined by the maximum number of iterations. And this is how one could imagine running our gradient descent with a while loop. At first glance, this while loop would seem to make sense. The condition for running the loop is run the loop as long as the step size is greater than the precision. The step size is always the difference between the new x and the previous x. So at some point, that calculation would get more and more precise, at which point we would exit the loop. Fair enough. But this is exactly the kind of code that risks running into the infinite loop problem. Because in the case where one isn't converging and the step sizes between the values get larger, this loop just continues running. So I'm not going to keep this cell around. I'm going to go to Edit, Delete Cell. And this is why the for loop provides quite a big contrast, right? It's got this safety net by forcing you to explicitly state the number of times it will run ahead of time. Now let's crank up that learning rate even more. I'm going to scroll back down here, and I'm going to increase our learning rate from 0.25 to 0.3. I'm going to leave everything else the same and rerun this thing. See what happens. This is our old friend, the overflow error. The result is too large. We've shot off to infinity and beyond. What this little exercise is showing us is how there's another quirk that we have to be aware of with our optimization algorithms. We, as the machine learning experts, have to choose an appropriate learning rate. So that begs the question, how do we know what the right learning rate actually is? Because as we've seen, if we pick a very large learning rate, then our algorithm doesn't converge. And if we pick a very, very small learning rate, then our algorithm might actually take forever. What do I mean by forever? Let me show you. I'm going to scroll back up where we've called our function. I'm going to change this again to something that doesn't crash our Python program. So 0.02. And then I'm going to copy this bit of code right here. So that's the code where we're calling our function and the code where we're plotting our first chart. Now, I don't like seeing that error, so I'm going to rerun this cell. And then I'm going to paste our code down here. Now I'm going to change this comment here. I'm going to call it run gradient descent 3 times. before we run it 3 times, let's run it 1 time. So here's what I'm going to do. Instead of having the max iteration set to 500 here, I'm going to set this equal to a variable. So I'm going to say n is equal to 100. And then instead of having max iterations set to 500, I'm going to set it equal to n. So I'm going to specify the maximum number of iterations up here. Then I'm going to change the multiplier from 0.02 to 0.0005. And then I'm going to add a precision. I'm going to make it quite precise, the calculation. I'm going to say the precision should be equal to 0.0001, comma, and then have the maximum number of iterations back here. And for the initial guess, I'm going to start off at 3. So this is going to be our first call to the gradient descent function. But instead of having this sequence unpacking code here, we're going to store all of this information in a single tuple. So this is going to be called low gamma. Gamma is often used for learning rate, so we'll call our tuple low gamma. Now let's change up the code for our plot. I'm going to change the comment here to plotting reduction in cost for each iteration. So this is going to be our goal. In terms of the figure size, we're going to go with a single plot. So I'm going to size this plot differently from before. I'm going to make it 20 by 10. So it's going to be quite large. And then I'm going to delete this subplot code here. We don't need that. And then for our axes, we're going to go on the y-axis, we're going to go from 0 to 50. So this is going to be our cost. Our cost is going to be on the y-axis. You'll see this in a bit. And our x-axis is going to go from 0 to the number of iterations. So it's going to go from 0 to n. And it's going to be 100. Going to have the iterations on our x-axis. So our x-axis is going to go from 0 to n. The title of the chart is going to be the effect of the learning rate. And for the x label, we'll have the number of iterations. And for the y label, we're going to have the cost. Now we need the data to populate our charts. So we need the values for our charts. And we need 2 things. The first thing is going to be what we have on our y-axis. That's going to require us to convert the lists to NumPy arrays. Reason being, we can feed an array into our g of x function, but we cannot feed a list into our g of x function. So we've done this previously. I'm going to call our first array low values. Set that equal to np array low gamma. And it was the second item in our tuple. Why did I just put a 1 there? Because the second item is at index 1, because we start counting from 0. The first item is at index 0. The second item is at index 1. Okay, so that's our y-axis data. Time to get our x-axis data. Now we just need our x-axis to go from 0 to like 100, right? So what we're going to do is we're going to create a list from 0 to n plus 1. Why n plus 1? Because we've got that extra initial guess. So even though our loop is running around 100 times, our extra guess is going to mean we should have 100 plus 1. And we're going to store this information in a variable called iteration underscore list. So how do we create a list in the past? Let me scroll down here a little bit. In the past, we've had our square brackets and we said 0, 1, 2, 3, right? We just populated that list with values. But this isn't what we're going to do because we're not going to type out 100 different values in this list. Instead of creating this list manually, What we're going to do instead is we're going to make use of this range function that we saw with the for loop. Our range has a starting value and an ending value. So it's going to create all our values from 0 to n plus 1. But we can't do it like this exactly. The reason is that if I press Shift Tab on this function, I can see that this thing here will actually spit out a range object. So this range function will give us a range object. But what we need is a list. So how do we convert a range object to a list? Well, we can call the list function and then nest the call to the range function inside our call to the list function. So now we'll have a list starting from 0 going to n plus 1 that's going to be stored inside our variable called iteration list. And this is what we're going to take, and we're going to put that right here on our plot. So I'm going to put that here, and then for our y-axis on this plot, we're going to use our, well, low underscore values. We're going to use our array of values for our cost function. And we also don't have to stick to the blue color. There's a lot of colors available, including like light green, for example. And we can make the line a bit thicker, change the line width from 3 to 5, and we're going to get rid of the alpha as well. Now I'm going to comment out the plot.scatter code and just show our plot for a change. So I'm going to say plt.show, parentheses at the end, and hit Shift Enter. See what we get. Ah, okay. So we get a nice line plot right here, just like this. So this is cool. But you know what? We're going to take our scatter functionality and use it as well. That way we get a little bubble each time our loop was run. So that way we can see the step size a bit more clearly. So our x-axis is going to be the iteration underscore list again. And for our y-axis, it was going to be our low underscore values array. I'm going to change it to the same color as with our line plot. So it's going to be color light green. And for the dot size, we'll change it from 100 to 80 and get rid of the alpha as well. So let me rerun this, see what it looks like. Aha. So this is pretty good. So larger step size in the beginning, getting smaller until the steps are very, very close at the end. So what we're looking at here is the decrease in the cost with each iteration of our loop. And I think this is really, really neat. But it'll be even neater if we can plot 2 different learning rates or 3 different learning rates on the same chart next to each other and see how they compare. So I'm going to scroll back up here, and I'm going to correct my typo in the title to have effect of learning rate with a space. And I'm going to add a little comment here as well. I'm going to say plotting low learning rate. And then I'm going to scroll back up to the beginning and put my cursor right here. Now, as a challenge, can you plot 2 more learning rates on our chart? So pause the video, add a tuple called mid-gamma, and keep all the inputs to the call to the gradient descent function the same, but change the multiplier to double the learning rate to 0.001. And then create another tuple called high gamma and change the learning rate there to 0.002. Now you're going to have to extract the values from the tuple that you get back and throw those onto our chart. I'll give you a few seconds to pause the video and give this a try. And here's the solution. So the quickest way to do this is to copy this code here, paste it 2 times, change the name of the tuple to mid-gamma, change the name of this tuple to high gamma, and then this multiplier is going to be 0.001. This multiplier is going to be 0.002. And then we're going to come down here take this code right here, copy it, paste it twice. I'm going to change my comment, plotting mid-learning rate, plotting high learning rate. And then instead of feeding the low values into our array here, I'm going to make a call to nparray and then put in our tuple mid gamma 1. I'm going to take this, copy it, put it here as well, mid gamma 1. And this is going to be nparray high gamma 1. And same with this one. It's going to be nparray high gamma 1. But one thing that I'm going to change as well is the color. I don't want all of these graphs to have the very, very same color. Otherwise, I can't tell them apart on the chart. One nice color to contrast the light green is steel blue. This is going to be for the slightly higher learning rate. And then for the highest learning rate on this chart, I'm going to pick my favorite color, hot pink. Why not? Now again, I'm not making these color names up, yeah? I'm taking them from the Matplotlib official documentation. So these are the names that I can put into that argument. So there's a predefined number of names that you can use, and the spelling has to match exactly, otherwise it won't recognize them. Okay, so I've got my charts. Now the proof is in the pudding, as they say. Hit Shift Enter, and let's see what we get. So I think this chart is beautiful because it illustrates so nicely how our learning rate affects our algorithm. We've run our gradient descent 3 separate times with different learning rates, and now we can see how the cost decreases with each iteration of the loop. And what we're seeing here is that the highest learning rate, the one in hot pink, converges the fastest. In other words, the higher the multiplier, the faster the convergence. And in contrast, we've got the really low multiplier converging very, very slowly to the minimum. Now, if we picked an even lower multiplier, then it would reach the minimum even more slowly. But as we've shown before, the higher multiplier is only better up to a point, right? Remember how in our earlier example, our entire graph was red? Clearly, having like a really high multiplier, you either get an overflow error or we don't converge on our minimum. So higher multipliers don't always work out. In fact, let's plot this crazy behavior that we had early on this chart as well. So I'm going to go up here and add a comment here, call it experiment. And then I'm going to take my Python code, copy it, paste it here, and maybe call this insane gamma. Now my initial guess was 1.9 in our earlier example, and the multiplier was 0.25, if I remember correctly. And now all I need to do is come down here, take this bit of code here, I'm going to paste it, and I want to modify it. So I'll read plotting insane learning rate, and this is going to be our insane gamma. And in terms of color, let's go for just good old red to show that this is not a good thing. Now I can hit Shift Enter and see how that behaves. So what have we got? Ooh, that looks really bad. So mind you, in our fourth example, we started out much closer to the minimum. We started out with an initial guess of 1.9, and that's compared to the initial guess of 3, which is where we started out with the other functions. So even though our initial guess was actually much better and our cost was much lower, it doesn't actually help us when our learning rate is all screwed up. So we can see here that our cost doesn't actually come down, even though that algorithm has been running 100 times. We just have our cost bouncing around, decreasing, increasing, decreasing again. And in the end, after 100 iterations, we can see that our cost here at the end is actually much higher than what the cost is for all the other examples. So all the other learning rates after 100 iterations had a lower cost even than our really, really high multiplier of 0.25. So I think that illustrates the problem really nicely when the algorithm is bouncing around with no clear direction. And I think a takeaway from this exercise is that picking the right learning rate is both a bit of an art and a science. And so it shouldn't come really as a surprise that there isn't really one perfect solution for picking a good learning rate either. So even if you go to the literature on machine learning, you'll find that there are different approaches for picking a good learning rate. Now, I've talked a little bit about two of the things that this optimization algorithm is sensitive to. These two knobs, right, that we could turn. The initial guess and the learning rate. And you might come away thinking that, gradient descent, it's a bad algorithm because it can have certain problems. And yeah, it has pros and cons, but one of the really, really big advantages of gradient descent is that it is incredibly simple. It is an incredibly simple algorithm, and it is also quite fast. So it's quite a fast thing to run to train your machine learning model. And that's an advantage that not every other competing algorithm can claim for themselves. So given its relative simplicity and speed, you can actually try out different learning rates for your cost function and see what works best. But of course, there's more elegant approaches to picking a learning rate as well. For example, we could adjust our learning rate while the algorithm runs, meaning the learning rate doesn't have to be fixed. The learning rate could chop and change after each step in our loop. So why would we do that, might you ask? Why would we have a learning rate that's not fixed for a particular value? Why would you want to update the learning rate every time the loop runs? Well, so the idea behind that is that the further you are from an optimal value, the faster you should move towards that minimum, and thus the ideal value of your learning rate should be larger. But on the other hand, once you start getting closer and closer to that minimum, then the learning rate should come down as well, because you don't want to overshoot. And this is why some machine learning practitioners create like a predefined schedule for the learning rate ahead of time. And in this schedule, the learning rate starts off large and then gradually gets smaller. But there's a whole host of like other techniques as well that people are using. For example, one quite simple technique is called the bold driver. And it works like this. If your error rate, your cost was reduced since the last iteration, then you can try increasing the learning rate by 5%. And if your error rate was in fact increased, meaning that you skipped over the optimal point, then you should reset the values of your parameters to the values of the previous iteration and decrease the learning rate by 50%. So you can see with this kind of rule how the learning rate would change. Increase by 5% if you had a reduction in your error rate, and go back one step and decrease the learning rate by 50% if you had an increase in your cost. Okay, wow, so this was quite a theoretical lesson, and we've covered quite a bit. We've covered how our algorithm is sensitive both to the initial guess and the learning rate, and now we can start to kind of tackle some more complicated cost functions. In particular, so far, we've only been working with estimating a single value, right? When you look at g of x, there's only one thing there. There's x, right? But this is only one dimension. Let's turn our attention to how we can tackle 2 dimensions in our gradient descent algorithm, and then you'll see how you can tackle more than 2 very easily. I'll see you in the next lesson. Have a good one.